Hi, class. So from what I remember, we got through all of section 3.6 except for the very end doing some applications. So I want to spend a few moments here just going over that with you so that way we can finish out the notes for section 3.6. So in section 3.6, there's this application section you can read. So it says if you throw an object directly upward, although its path is straight and vertical, its changing height over time can be described by a quadratic function, right? So this changing of the height, as you can imagine, has to do with gravity, right? It's like pulling down on the object, so it's going to have some kind of like quadratic shape, right? So even like if you throw a football, right, it's gonna, it's gonna have some kind of path like this, right, which is partly like a quadratic type of shape, right? So even like a bullet, right, everything is going to have kind of this quadratic shape to it. Some are more extreme than others, right? So what this chart tells us is it gives us a quadratic equation where if we know the initial velocity of the object and also the initial height, right, then we can plug it in and have this equation where s of t is the height above the ground and t is the time that it's in motion in seconds, right? So you can see that when you see this v naught, right? So that's where's that defined? Right here, right? So that's the original velocity or the initial velocity, right? So a lot of times in math, when you use a subscript O, 0, that signifies initial, right? So then like s sub 0, right? That corresponds to the original height, right? The initial height of the object in feet, right? So then we can plug, if we know those items, we can plug into this equation, and then we can have a quadratic, right? So then at the bottom of these pages, these two graphics we're going to use on the next example. I threw them here to save some space. I figured we would need more room to write, right? So I'll refer back to those as needed. So the example that we're looking at, it says a ball is thrown vertically upward from the top of the Leaning Tower Pisa, which is 190 feet high, with an initial velocity of 96 feet per second. During which time period will the ball's height exceed that of the tower, right? So you could try to draw a picture of this, right? So essentially we have this tower, which is 190 feet high, and we're throwing a ball upward, and as you can imagine, it's going to have like this quadratic shape and go until it hits the ground, right? Where this is the ground. And then so this was the initial height of the object is 190, right? So s sub naught would be 190, that would be feet, and then the initial velocity is 96 feet per second, right? So then if you want maybe a prettier picture, right, if you will, that's what this book is representing. Right, so here's the tower, here's the ball being thrown. It's 190 feet from the tower, and what we're after is when is the ball exceed that of the tower, right? So in other words, we're after how long is the ball in this dash part, right? We don't know when it's above the tower, essentially, right? So if we plug in our known constants into the equation, we would have s of t equals negative 16t squared plus, let's see, well, it'd be the initial velocity, but we know that's 96, right? So that's v naught, right? And then we would have that's times t, and then plus you would have s sub naught here, which we know is 190, right? So this is my equation to represent the height of the ball after t seconds, right? And notice it's a quadratic, right? It's a degree 2 polynomial. So the reason why this is in this section to be an inequality, right, is because we're interested when is the height of the ball above 190, right? So we're after, let me just change the color. We're after this part here, right? We want to know the time that it's in this part, right? So so S of t, we would want this to be greater than 190, right? Is really the question. So if I substitute this in for S of t, right, the right hand side of my equation, then I would get an inequality that I'm trying to solve, right? I'm trying to figure out when is minus 16t squared plus 96t plus 190, when is this bigger than 190, right? So something really nice here is if I subtract 190 from both sides, notice that these terms cancel each other out, right? We're left with minus 16t squared plus 96t greater than 0, right? So they're inequality. So remember, this is an example of a polynomial inequality. So we need to figure out where are the zeros of the function, and then place those on our point, our line chart, right? Our sign chart, to be able to tell what intervals makes this inequality true, right? So one nice thing would be is if this factors, and then we could find those zeros pretty easy. So if I pull out a negative 16t from both sides, or not from both sides, but from both terms, I would have t minus 6 inside, right? Because 16 times 6 gives you 96. So this would be greater than 0. So then from this, I can easily find that my values would be t equals 0 and t equals 6, right? Those would be the zeros of this function, right? In other words, we're trying to solve when is this equal to 0, right, to be able to find these values, find these zeros. So then I take my number line, and I'm going to plot these, right, 0 and 6, right? And then I want to pick some test values inside each of these regions. So for example, to the left, I plugged in minus 1 into f, and or I guess we're not using f, we use t, right? So let me be consistent. So I plug this into the s function, right? So s of negative 1 would be negative 112, right? So this region is negative, right? In other words, s of t is less than 0, right, in this region, right? I can just make some dashed lines here to separate these. So then if I want to pick a point inside of here, right, you could pick anything between 0 and 6. So I picked 1, right, just to make that easy. So if you plug 1 in, you should get 80, which this means that s of t is going to be greater than 0 in this region, right? In other words, it's positive, right? And then inside this region, we would have, so I plugged in f, again, it's not f, sorry. Get in the habit of using the f function too much, right? So we're using the s function, right, is what the function we were using. So if you plug in 7 into s, I got negative 112, right? So in other words, in this region, s of t, right, is less than 0, right? So if we go back up to what we were trying to find, right, so looking at looking at it in this form, right, what we're after is when is our function greater than 0, right? Wait, excuse me. We shouldn't be plugging these into S. That's so I was doing. Whoops. Sorry about that. So I was doing this right. I was second guessing myself, I guess, or something. So let me go back up to here, right? So when you get to this step, right? Remember the whole idea is we're trying to get our function into one of these forms. Right, as we did before. So notice at this point, I have my function in this format, right? So in other words, if we let f of x be equal to negative 16t squared plus 96t, right? Then what I'm trying to solve the inequality is when is f of x bigger than 0, right? So then what I found is these are the zeros for f of x, right? So then I should be plugging in these values into f, right? Not s. Right? Right? So that gives you those values, right? And if it makes sense, if you want, you could graph this in your graphing calculator, right? Just to reiterate what we're doing, right? So if we look at the original graph, right? S of t, I'm going to put that in y1. That was negative 16 t squared. So I'll just use x instead of t. X squared plus 96x plus 190, right? So then I want to graph that and also graph 190, where y equals 190, right? So I'm going to need to adjust my window. Let's see. Let's do negative 2 to 8, going up by ones. And for y value, let's go 0. Let's try 100. See if that will give us a complete graph. That doesn't. We need to go higher, right? So notice I can tell like the vertex is way up there. So I don't know. Let's try 200. Oops, still not high enough, right? Try 300. Maybe we'll go up by 20s then. Oops, still not high enough. So do 400. There, right? So now we're getting a pretty complete graph, right, of the inequality, right? So really what I'm trying to find is when is this, what's this point and what's this point, and obviously the ball is going to be above the red line, in between those two times, right? So what you could find is like an intersection between those two points, right? But basically what we were doing with the inequality by setting it equal to 0 by subtracting 190 from both sides, right? What do you do when you subtract 190 from a graph, right? You're shifting it downward, right? So if I go down here and graph negative 16 x squared plus 96, oops, should be 96x. Right. So notice what happened is this point just went down 190 units, and this point went down 190 units, right? So in other words, instead of these 2 points touching the red line, we made them touch the x-axis, right? But all these points just shifted downward, right? So then that's when we find the zeros, right? Because that's where it can possibly change from positive to negative. So we found those zeros. Let's see where. Oh, here, right? We found that t equals 0 or t equals 6, and that's what those values would be, right? And you could double check, right? We could go to second calculate the option 2, right? The zeros. So we want to do this function. So we just have to go to the left, go to the right, and then try to get right in the middle. And you can see we get the 0.00, right, which is one of the x values we had. And then you could find the other one. Right, so again on the black curve. Right, so we need to go to the left, then go to the right, and then try to get right on it. And we get 6 for the other x value, which is what we got algebraically, right? So that backs up our answer. So then if I change my window a little bit, so maybe for the y, let's go down to like negative, I don't know, 100. Let's see. Right? So then basically what we did is we tested some points, right? So then like here I plugged in -1 into the function, so -1 was down here to -112, and that means that the graph's negative down here, right? And then when I plugged in f of 1, so f of 1 would be here, this point, that we found that to be 80, and that was positive, right? So it means this region's positive. And then we needed something beyond the next 0, which we plugged in 7, which would be here, and this y value was negative, right? And we could look at a table. So let's say we want the table to go from, we could just do -1 to 1, and going up by 1 each time, then we can get those values, right? So if I plug -1 into my f function, we get -112. If I plug 1 in, we get 80. If we plug 7 in, we got the -112, right? Which is consistent with the values I had here, right? So just trying to extend that a little bit, and why that makes sense, right? And sorry for messing up that notation for a minute there. Right, so hopefully that clears that up and makes more sense. If not, I'll be glad to help you on Thursday during class. Right, but then so remember what we're trying to find is when is f of x bigger than 0, right? That's ultimately what we're trying to find. So in other words, when is it positive? And that's in this range, right? So my solution set would be 0 to 6, not including 0, not including 6, right? So this would be the solution, right? In interval notation, if you wanted to use set builder notation, right, we would say any x such that x is in between 0 and 6, right? So you could show either one of those. And then lastly, if we had to graph this, right, let me grab a different color. Right, if we had to graph this, we would have a parenthesis at 0 and 6 and shade in between, right? Or of course, like we've done before, you could use, oops, didn't mean to hit that. You could use an open circle, right, and then shade in between. So either one of those would be, these would be a graph, right, of the solution, right? So the ball is above the building from 0 to 6 seconds, right? So hopefully that makes sense. So this wraps up chapter 3, and then I am posting another video for section 4.1, and then so So I'll post more directions on Canvas about that too as well. All right, thanks.